Welcome, future structural engineers, to this explainer on the foundational concepts of the IS 800-2007 Steel Design Code. If you're stepping into civil engineering, you're going to hear about this document a lot. Today, we're cutting through the dense technical jargon to focus purely on the conceptual clarity you need to design safe, economic steel structures. So, let's just dive right in.
Right off the bat, let's ground our explainer in the official documentation. You're looking at the emblem of the Bureau of Indian Standards, or BIS. They're the authoritative body that publishes IS 800, officially titled General Construction in Steel, Code of Practice. This document went through its third major revision in 2007, and honestly, it is the absolute baseline for structural steel design in India. Literally every calculation you make, every single steel beam you size, traces its fundamental logic back to this very rulebook.
Here is our agenda for today. First, an introduction to IS 800-2007. Second, limit state design philosophy. Third, understanding safety factors. And finally, steel section classifications.
All right, Section 1, Introduction to IS 800-2007.
The crucial word to focus on here is general. IS 800 is your prime document for general construction in steel structures. Think hot-rolled steel sections joined by riveting, bolting, and welding. But, it's absolutely crucial to understand its boundaries. It provides general guidance. If you're designing highly specialized structures like bridges, towering chimneys, heavy-duty cranes, transmission line towers, or cold-formed light-gauge steel sections, well, IS 800 steps back. Those require their own highly specialized standards. Plus, while it tells you how to design the steel itself, it only gives broad guidance on the actual loads. For specific dead, live, or wind loads acting on your building, it's going to direct you to reference IS 875. Think of IS 800 as your master rulebook for steel behavior, while those other codes fill in the specific environmental demands.
Moving on, Section 2, Limit State Design Philosophy. So, we need to define what a limit state actually is. According to the standard, a limit state is the acceptable limit for safety and serviceability requirements before failure occurs. The ultimate aim for us as engineers is to achieve an acceptable target reliability. In plain terms, we want the probability of a limit state being reached during the structure's entire lifetime to be incredibly low. We design the structure so it won't become unfit for its intended use. That means ensuring it doesn't collapse under a heavy load, which we call a safety limit state, or ensuring it doesn't crack or deflect so much that it completely terrifies the people inside, which is a serviceability limit state. You always design for the most critical limit state, and then you double-check the others.
To make this whole philosophy work mathematically, we have to contrast two really important concepts: characteristic values versus design values. Characteristic values are essentially our raw data. They're based on statistical averages for material strength, like how strong a specific batch of steel actually is, and applied loads, like the historical maximum wind speed in a particular city. But listen, the real world is unpredictable, right? We literally can't design a building right on the razor's edge of statistical averages, and that is exactly where design values come in. We derive our final safe design values from those characteristic values by applying partial safety factors. This builds our mathematical safety net.
And that perfectly brings us to the golden rule of structural design. Design action must be less than or equal to design strength. Seriously, write this down, memorize it, internalize it. This simple, elegant inequality is how structural reliability is actually ensured in the real world. The design action, meaning the total factored loads pushing, pulling, and twisting your structure, must mathematically remain lower than the design strength, which is the factored, reliable capacity of the steel to resist those forces. Every single complex formula in IS 800 basically boils down to proving this one statement is true for every single beam, column, and bolt.
Okay, Section 3, Understanding Safety Factors.
To enforce that golden rule we just talked about, the code dictates the use of partial safety factors. We apply these to account for real-world statistical variations in both the materials we buy and the unpredictable loads nature throws at us. We have partial safety factors for the load itself, artificially inflating it just to be on the safe side. Then, we have partial safety factors for the material, slightly reducing its assumed strength to account for potential manufacturing imperfections. And the code gets really specific here. There are unique factors for yield stress and buckling, for ultimate stress, and even different factors depending on whether you're using a standard bearing type bolted connection or a high-strength friction grip or HSFG bolted connection. This level of granularity is exactly how the code ensures economy without ever sacrificing safety.
Now, I want to pose a critical engineering question to you. What happens when a steel element buckles before reaching its yield stress? Think about a plastic ruler for a second. If you compress it from both ends, it doesn't snap from the compression, right? It bows out to the side long before the plastic actually fails. Well, steel can do the exact same thing under compression. This physical reality forces us to pivot from abstract mathematical safety factors to looking really closely at the actual physical geometry of our steel members.
Which leads us to Section 4, Steel Section Classifications.
Understanding this specific classification is vital for any structural engineer. IS 800 categorizes sections based on whether their thin plate elements will buckle locally when compressed. Let's walk through it. A Class 2, or compact section, is sturdy. It can develop its full plastic moment of resistance, meaning the entire cross-section yields, but it's going to buckle locally before it can rotate enough to form a full plastic mechanism. Next up, a Class 3, or semi-compact section, is slightly thinner. The extreme outer fibers in compression can reach their yield stress, but the section will buckle locally before the whole cross-section can reach that plastic moment capacity. And finally, we have Class 4, the slender section. These elements are so thin relative to their width that they will buckle locally even before the steel reaches its yield stress.
Because Class 4 slender sections buckle so early, the code highlights a very specific design workflow for them. If you're dealing with a slender section, you absolutely cannot just use its full geometric area in your strength calculations. The engineer has to either use specific provisions to account for post-local buckling strength or, much more commonly, mathematically deduct the excess width of the compression plate element that's prone to buckling. You essentially have to pretend a portion of the steel simply isn't there, calculating what's known as an effective section to ensure your design remains safe.
Let's tie this all together. What we've seen today is that limit states set the goalposts. Partial safety factors give us the mathematical buffer for the unknown, and section classification ensures we respect the physical reality of local buckling. To sum it all up, mastering these interconnected concepts is the absolute key to safe, efficient, and economic construction in steel, exactly as intended by the IS 800 code. I want to end this explainer with a provocative thought for you to carry into your actual load calculations. Imagine you selected the perfect Class 2 compact section. It's robust, it won't buckle early, but due to a massive oversight, the partial safety factors for the applied environmental loads are completely ignored in the design. How quickly does our fundamental golden rule of design action less than or equal to design strength completely break down when an unexpected storm hits? Engineering isn't just about picking the right shape, it's about rigorously respecting the entire philosophical framework of the code. Keep that in mind as you move forward in your structural engineering journey, and thank you for joining me on this explainer.